Now that you've had a basic introduction to public cloud networking, we'll now take a closer look at AWS with an introduction to public cloud networking in AWS. My name is Brad Hedlund. I'm a Principal Solutions Architect at Aviatrix, and before joining Aviatrix, I was at AWS for 6 years, helping customers and partners to optimize their AWS infrastructure and helping them to architect their AWS networking environment. So the very first thing that you need before you can do any networking in AWS, or really anything for that matter, is an AWS account. So if you don't have an AWS account, you can go to the AWS website and begin the sign up process. And in doing that, you will provide an email address, the root email address for that account. And that root email address is really the first user of the account, and it has ultimate permissions. So a best practice would be to secure and lock that account down after you've got your account all set up. Now that I've got my account set up, I will have an AWS account number, and I can go ahead and sign into my account using that account number. And if I've set up some IAM usernames, which I'll explain later, in this case I have, and I will sign in with my IAM username and password. And then of course I can log into my AWS account through my web browser. Now, once I've done that, I will be presented with the AWS console. So let's take a closer look at what that console looks like. So here I'm at the console, and once you're in the console, you can pick from any number of AWS services to go into that area of the service to begin configuring them. I just happen to be in the VPC section of the console, where I can create VPCs and subnets and route tables and internet gateways. Now I have access to all of the AWS regions, so when I'm creating a VPC, I'm going to do that in a very specific region. I just happen to be in the US West Oregon region right now, so any VPCs that I create will only be in Oregon. If I want to create VPCs in another region, I will pick that region from this drop-down list here and then go create my VPCs and subnets and route tables using the console and do it all in that region. Okay, I've got my AWS account now and I'm signed in. So let's take a closer look at what is inside this AWS account and what are some of the important things that I need to know about it. And why would I want to have more than one AWS account? Why is one account not enough? And we will take a look at that here. So first thing is AWS Identity and Access Management is where I go to create usernames and roles and give those users and roles permissions to do things. There's going to be more than one person using this account probably, and I don't want everybody to be logging in using that root email address that I used to sign up for the account with, because that's a very powerful login. So I want to lock that login down, and then I want to create usernames and give people access that way. So for example here, Danny might be a part of the DevOps team. So we'll give Danny permissions to launch EC2 instances and use other AWS services that are related to the DevOps function. Jenny, on the other hand, is part of the network team. So we'll go ahead and give Jenny permissions to create networking constructs like VPCs and route tables and security groups and subnets so that she can build the network within this account and between other AWS accounts. Now, every AWS account is going to have its own AWS bill. So all the services that the users using this account use will be charged to an AWS bill that is specific for this account. And all of the VPCs that Jenny creates as the network administrator, well, those VPCs will be in this account only and only live in this account, unless, of course, she enables VPC subnet sharing and shares one of the subnets from a VPC to another account. I'll discuss that later. And importantly, every account has service limits. So a service limit is basically a quota on the number of things you can do with a certain service, such as the number of EC2 instances that you can launch in a VPC, or the number of VPCs that you can create in a region, or the number of peering connections that you can have from one VPC to other VPCs. Some of these limits are soft limits, and they can be raised if you ask AWS to raise them for you. Other limits are hard limits, and they cannot be raised. And you have to work and architect around some of those hard limits, and we will see examples of those hard limits later in this session. Now, in a larger enterprise, this might be a particular business unit that Danny and Jenny are a part of. And other businesses within the enterprise want to start using AWS as well. But business unit A here does not want to have any other business unit using their AWS account because they don't want them racking up their bill and racking up their service limits. So the other business units are all going to create their own AWS accounts. And they're going to have their own IAM usernames and roles and permissions. Each account will have its own AWS bill to rack up the costs in that AWS account, and each bill needs to be paid individually. Any VPCs that are created are only within the specific AWS account. And of course, the service limits are in this individual account as well, and only account against the services that are used in this account. So you can see that there is a nice separation between these two business units because they are using two different AWS accounts. And that extends into other environments in the organization, such as using multiple accounts in production and development and test and QA. There's a nice isolation and separation there. So for example, a developer working in a dev account might make some big mistake and break something, but that's not going to affect anything running in the production accounts in the production environment. So in a larger enterprise, you are going to see a lot of different AWS accounts across a lot of different business units, across a lot of different environments in that account. And one of the challenges that comes from that is how do you manage all of the permissions and policies across all these accounts? How do you manage all of the AWS costs and bill? How do you manage all of the AWS networking through the VPCs and so on and so forth? So managing a large number of accounts can be quite challenging. And in the next slide, we are going to show you how to do that using AWS organizations. Now, within your company, you're going to have lots of different AWS accounts, and you can manage them all together using AWS organizations. So with AWS organizations, I will create an account and deem that the management or administration account, and that is where I will use the service AWS organizations. And the first thing that I'm going to do in organizations is define organizational units. So these would be logical groupings of AWS accounts. So in my example here, I've got 3 different business units, so I'll go ahead and create 3 different organizational units, one for each business unit. And that becomes a logical container for the accounts that those business units create. So when somebody creates an account in one of these business units, I will invite that account into the organization, and they will be part of the overall AWS organization. Now, one benefit from this is now we will have a consolidated AWS bill. So all of the costs that are generated in all of these different accounts across the different business units will all be rolled up into one consolidated AWS bill. So that's a lot easier to manage rather than having to worry about all of these different accounts with all their individual bills and making sure all of them are getting paid. Now, from a policy standpoint, you also have service control policies. So while each individual account does have IAM usernames, roles, and permissions, I can establish some higher level policies at the organization level using service control policies that will override any IAM permissions in any individual account. For example, as a company, I may not want anybody to use any AWS services in a certain country. So I could write a service control policy that denies the use of certain AWS regions and apply that down. So no matter what the IAM policy is in an individual account, the service control policy will override that and prevent the use of the regions that I don't want people to use. Now, once I've established this organization, you can begin to share resources between accounts within the AWS organization. One example is sharing VPC subnets. Using AWS Resource Access Manager, you can take a VPC in one account, pick a subnet, and you can share that subnet to another AWS account. And then the users of that other AWS account can launch resources into that VPC subnet. They maintain ownership of their resource in that VPC subnet, but the account that is doing the sharing of the VPC subnet still owns and manages the VPC itself. So that's one example of how you can share resources between AWS accounts, among many others. From a single AWS account, you can run AWS services anywhere in the world where there is an AWS region, shown as dots on the map here. An AWS region is really a place in the world where AWS has built data centers and organized them together into an AWS region. The AWS regions are connected together through the AWS Global Backbone, but that doesn't mean that if you have a VPC in two different regions that they can just automatically talk together. You will have to build all of that connectivity yourself in your own AWS account. Now, AWS has designed the regions so that they are separated from each other from a failure standpoint. And what that means is one region could be experiencing some sort of failures or even completely fail, and it's not going to affect the services in any other region. Now let's take a closer look at what a region really looks like and take a look at it from the standpoint of networking. So a region is made up of two or more availability zones. And each availability zone is made up of one or more AWS data centers. Now, all of the data centers that are in the same availability zone are all in the same failure domain. That means that they could experience a power failure. They're all drawing power potentially from the same power grid, so they could all fail together from a power failure. They might be in the same floodplain or in the same tornado area and experience a localized disaster. So that is why AWS builds multiple availability zones to form a region so that the region has higher availability. So the second availability zone or third would be further away from the other availability zones and not in the same floodplains and not in the same tornado area and drawing power from a different power grid. Now, all of the availability zones are connected to the AWS global backbone as well as to the internet. So when you create a VPC in a region, you can pick which availability zone you want to run a service in by simply creating a subnet in that availability zone and launching your EC2 instances in that subnet. As a best practice, customers will build and run their applications to span multiple availability zones so that if one availability zone were to fail due to maybe a power failure, their application is still available in the other availability zone. So now let's take a look at the AWS VPC and how that maps to the availability zones. The fundamental networking construct of AWS is the VPC, Amazon Virtual Private Cloud. Now I first need to have an AWS account, and when I create a VPC, that VPC will only exist within my AWS account. Now I need to pick a region because a VPC only exists within one region. So I'll go ahead and pick any region in the world, and then I'm ready to create my VPC. Now, as I explained earlier, a region has multiple availability zones. And the good thing is that my VPC is going to span all of the availability zones in the region. So now I'm ready to create my VPC. And a VPC is a virtual network that I can define, and I can assign my own address space, private address space to this VPC that I want. In this case, I'll assign 10.100/16 to this VPC. That is basically the network range that belongs to this VPC. I can also have Amazon assign an IPv6 range to this VPC if I want to. Now that I've got my VPC, the next thing to do is to create VPC subnets. And a VPC subnet only exists within one availability zone within the region. So when you create your first VPC subnet, the first thing you're going to do is pick which availability zone you want that subnet to exist in. You can see here that I've created 4 subnets, and I've given each subnet an IP range that is a subset of the overall VPC range that I assigned. Now I can launch EC2 instances into these subnets, and the EC2 instance will get an IP address from the VPC subnet range that I assigned it. You can have many VPCs in your account and in a region. There is a default limit that I explained earlier, and that default limit is 5 VPCs per region, but that's just the starting limit, and it's a soft limit, so you can raise that by asking AWS to raise that limit for you, and you could have many VPCs within a region, could be hundreds of VPCs. There is something called VPC flow logs that I can enable on this VPC too. And what flow logs is going to do is it's going to keep a record of all of the traffic that is going between EC2 instances in this VPC or traffic coming in and out of this VPC. So I can see a list of all of the sessions that have been taking place so that I can maybe later analyze and visualize that data. I'll explain that on the next slide. Okay, once I've enabled flow logs, let's talk about what it's going to take to get visualization and search capabilities of all of that flow log data. Now, as I explained earlier, an average enterprise is going to have many AWS accounts. And in each AWS account, you could be operating VPCs in multiple regions. So if I enable flow logs in each VPC, in each account, in each region, I'm going to have flow log data in all of those places, in each account, in each region. And the flow log data is basically a stream of text. That is all it is just text of all of the flows and all of the sessions that are going between EC2 instances and in and out of a VPC. Now, if I want to get search capabilities, if I want to type in an IP address and see what other sessions it's talking to, or if I want to visualize a chart, the first thing I'm going to need to do here is to aggregate all of this text data into a single place where I can then begin to run some visualization tools against it and maybe run some query tools. Now, this data aggregation and visualization and query is not something that you get just by turning on VPC flow logs. This is something that you need to go and build and manage however you want to do it. And AWS does provide you a number of different services that you can put together yourself to put together a visualization and search capability here. So you can use things like AWS Lambda and QuickSight. You can use Kinesis and Athena. Athena is a search tool. You can store all of this data in Amazon S3 storage. You can see some metrics in Amazon CloudWatch. There's a lot of different pieces of the puzzle here that you put together. This is a image from an AWS blog post on how to get visualization and search capabilities out of your flow log data. You can see that here's the puzzle being put together, and they give you a guide on basically how you're going to do this. You're going to send your flow logs to CloudWatch logs, and then CloudWatch logs is going to send that to Kinesis Data Firehose, and Firehose is going to send it in a number of different directions for different things to happen, such as creating custom metrics through Lambda functions and CloudWatch metrics, but you can see those in a dashboard, storing all of that VPC flow log data into an S3 bucket. So you'll set up Firehose to send it to an S3 bucket, and then you can use Athena, Amazon Athena, to run SQL-like queries against that flow log data. So if you understand how to build a SQL query, then you can start to search your flow log data. And then you can use Amazon QuickSight to get some visualization metrics of this as well. All right, let's go back to the VPC now, and let's talk about elastic network interfaces. Now, a server needs a network card to talk to the outside world, obviously, and an EC2 instance in AWS is no different. So you can think of the Elastic Network Interface as a network interface, network card for your EC2 instance. When you launch an EC2 instance, you'll get an ENI created for you and attach that EC2 instance automatically, and it will receive an IP address from the IP subnet range that it's attached to. You can also create your own ENIs and assign an IP address that you want on your ENI, and then you can go and decide which EC2 instance you want to attach it to. And the nice thing about these elastic network interfaces, and really the reason why they're called elastic, is because you can detach these ENIs from one EC2 instance and attach them to another. One scenario would be if you had an ENI attached to an EC2 instance that failed, well, you can just detach that ENI from the failed EC2 instance and then attach it to another instance that is already running. And that way now you have the same IP address available now on a different EC2 instance. You can also have a public IP address assigned to your ENI, and that is called an elastic IP address. So if you want your EC2 instance to be reachable from the internet, you would request an elastic IP address, and then you would associate that elastic IP address to your ENI that's attached to this instance. And now your instance will basically have a public IP address on the internet. You can have multiple ENIs on an EC2 instance, and the number of ENIs that you can have depends on the EC2 instance type and size that you are using. Usually the larger instance sizes can have more ENIs, the smaller ones fewer. Now, your EC2 instance and its ENIs can all be in the same availability zone, but they cannot be in different availability zones. In fact, you wouldn't even be able to do that. You would receive an error in the console if you tried to do that. Each one of these ENIs has an ENI identifier, and you will use that ENI identifier in VPC route tables, and I will explain VPC route tables in a few slides. All right, now let's talk about VPC security groups and network ACLs. We will use security groups and network ACLs to control and restrict network traffic to and from our EC2 instances and our VPC subnets. Security groups protect the EC2 instance. They are attached to an ENI of the EC2 instance, and they are required. When you launch a new EC2 instance with its ENI, you must have a security group associated with that ENI. Now you can have many security groups associated to the same ENI, and you can have many EC2 instances and their ENI all in the same security group. With a security group, what you do is you write allow rules. So all traffic is really denied by default, and what you do is you write inbound and outbound allow rules. Now, when you create a security group, by default, there is an outbound allow all rule already there, and there is no inbound rules. So again, by default, all traffic from an instance will be allowed outbound, but no traffic will be allowed inbound to that instance if you have not done anything with your security group at all. So at this point, what you do is you begin to write inbound rules to allow things from the outside world or other EC2 instances to communicate with the instance that's in the security group. Now these allow rules are stateful. So as traffic is processed by an allow rule, the security group will keep track of that connection, and it will allow return traffic, both directions of the traffic, to be processed. So for example, if you're allowing everything outbound from your instances in a security group, when they create a connection to something in the outside world or another EC2 instance, the allow rule will keep track of those connections and allow the return traffic for those specific connections to come back to your instance, even though you don't have any inbound allow rules. So the security group will handle all of that for you because they are stateful. And when you're writing these allow rules, either inbound or outbound, you need to specify source addresses. For example, in an inbound rule, you'll specify what source address applies to this rule, or with an outbound rule, you'll write destination addresses that the rule applies to. You can use IP addresses for those source or destinations, or you can use security group IDs. So for example, you could say, anything from security group number 1 is allowed to send inbound traffic to anything in security group number 2. You would write that rule in security group number 2. Now let's talk about network ACLs. So network ACLs protect the VPC subnet. So any traffic that's going into or out of a subnet itself will be inspected by a network ACL. When you create a VPC subnet, a network access control list will be created by default, and it has all allow rules by default. It has inbound rules and outbound rules, and by default there is an allow all rule that really just allows all traffic. Now, unlike a security group, you can write deny rules if you want to. So you can write both allow and deny rules, and these rules are stateless. Unlike a VPC security group, you will have to write allow rules in both directions if you want to have a bidirectional communication. Network ACLs will not keep track of any of the connections, unlike a security group. And in your source and destination, so for an outbound rule, you'll reference destination IP addresses. And for inbound rules, you'll reference source IP addresses. Again, you can use IP addresses, either specific ones with /32 addresses, or you could use site ranges like a /16 or a /24. Let's take a look at an example here. So let's say that instance B wants to talk to instance C in private subnet number 1. For that to happen, do I need to write any outbound rules in security group number 1? Well, by default, no, because there's already an allow all outbound rule there. So I didn't have to do that. Now in security group number 2, I did have to write an inbound rule that allowed traffic from security group number 1 for this communication to work. Now let's think about what happens when instance C wants to talk to instance D. So basically traffic between two different subnets. As that traffic begins to leave private subnet number 1, it will be inspected by the network access control list that's attached to subnet number 1. And by default, it has both inbound and outbound allow all rules. So if I haven't done anything special with this network ACL, if I've left everything at default, it's going to allow that traffic. So now this traffic will enter subnet number 2, where it will again be inspected by a network ACL that is attached to subnet number 2. And with everything at default, I didn't do anything special here. The inbound and outbound allow all rules are just going to let this traffic go through. Now the traffic arrives at security group number 3 because instance D is in security group number 3. And if I didn't do anything here, if I didn't write any rules for security group number 3, this traffic will be blocked because, again, by default, there are no inbound allow rules. You have to write them specifically. So this traffic would be blocked, and this is what you will find happen in many cases when two EC2 instances cannot talk to each other. In many cases, it will be that their security group is missing a rule or has a rule misconfigured. And this can be complex to manage at scale when you have many accounts and many VPCs and many instances with many security groups. Having to track down the right security group to fix the right rule can be not an easy thing to do, but nonetheless, if you are managing a AWS network, these are things that you will have to do to perform those troubleshooting tasks. Okay, now we are going to talk about VPC route tables and internet gateways and NAT gateways. A VPC route table is a very important construct of your VPC because the VPC route table directs traffic out of your subnet to its destination, and it is required. You must have a VPC route table attached to a subnet, and you can only have one route table attached to a subnet. So a route table contains a list of destinations and where to get to that destination. It provides a pointer to the next hop. A route table by default is going to have this local route, which is really just saying, look, anything going to the local VPC IP range here is basically local, and this just allows communication to happen between and within the subnets within this VPC. Now you can have many route tables in your VPC, but you can only assign one route table to a subnet. But I can use these route tables to treat different subnets differently in my VPC. For example, I might want to have a public subnet. So a public subnet is one that has a route table attached to it, and that route table has a default route to an internet gateway. So I created this internet gateway and I attached it to this VPC, and now I have a route table with a route to that internet gateway, and I attach that route table to this subnet, and that makes this a public subnet. The EC2 instances in this subnet can have public IP addresses, and those public IP addresses are really directly reachable by the internet, thanks to this route in the route table pointing to the internet gateway. Now I can also have private subnets with EC2 instances that can access the internet. I might need that for these instances to download patches and updates or access code repositories, but I don't want them directly accessible from the internet. So what we will do now is we will create a NAT gateway, NGW. So I can create a NAT gateway in the VPC console and attach it to this public subnet. And then I can have a route table with a default route pointed to the NAT gateway and attach that route table to this subnet here. So this makes this a private subnet because yes, it does have a route to the internet, but it's through a NAT gateway and not the internet gateway. The NAT gateway is going to prevent any connections from the internet initiating into this private subnet. So that still makes this subnet private. And the EC2 instances in this subnet do not need to have public IP addresses to reach the internet because as their traffic goes through the NAT gateway is going to translate their address into a public address that the NAT gateway is using so that it can reach the internet using the NAT gateway's public address, not the EC2 instance's address. One thing about these NAT gateways and the internet gateways is they will forward traffic to the internet without asking any questions about where that traffic is going. So these EC2 instances can access really anything on the internet. If you wanted to have more security to lock things down with a list of domain names that only these EC2 instances can access, you would not use the NAT gateway for that. You would have to use something else that has more security features. Now, another new capability that AWS has added with the VPC route table is something called a more specific route. So while there's always been this default kind of local route here for the VPC CIDR range, what you can now do is add a more specific route than the local one, like a route to a subnet within the VPC and point it at a next hop, such as an elastic network interface. So for example here, with this route table, it has a more specific route to the subnet 10150 over here, and it's pointed to ENI 123, and I've attached it to this subnet here. That means that if this EC2 instance in private subnet number 3 wants to get to private subnet number 1, it will read the route table here as that traffic gets to the subnet, and that route table will direct the traffic to ENI 123, which happens to be over here attached to this EC2 instance in private subnet number 2. A good example of this might be some kind of inspection device like a firewall or other intrusion inspection device of some kind that I want to inspect the traffic before it gets to this instance up here. So that is a way to direct traffic within your VPC through an inspection appliance using what's called a more specific route. Now with route tables, you can have a lot of them across a lot of accounts and a lot of VPCs. And the route tables largely are not dynamic. That means you have to manually configure the routes in these route tables, except for the situation where you are using a VGW with route propagation, and I'll explain that on the next slide. But for the most part, VPC route tables need to be manually configured. And just like a security group, they can easily be misconfigured. So you can have a lot of these route tables and a lot of subnets. And if one EC2 instance is not able to talk to another and you've verified that the security group rules all look good, chances are you have a misconfigured route in a route table somewhere. And sometimes it can be difficult to find the right route table and check if it has all of the proper routes when you're dealing with a larger environment. And this is a screenshot of what a VPC route table looks like in the AWS console. So here I have a route table in my account and in my VPC. It is associated to a certain VPC here. And I have associated this route table to 2 different subnets. So yes, you can have one route table associated to many subnets in your VPC, but each individual subnet can only be associated to one route table. Now, if I look at this route table, I see that there are destinations here, and those destinations are pointed to a target. So if I'm trying to get to any one of these address ranges, this route table is going to direct traffic from that subnet to these targets here. And here what I have as a target is an ENI for an EC2 instance in this VPC. So that tells me that this is some sort of routing instance or some sort of security instance maybe that I want the traffic to go through before it gets to this destination here. You can also see that there is this default local route here. So this is basically the local address here assigned to my VPC and everything's local. That route is always there. You can also see here that I've got a default route to an internet gateway. So that means that any subnets that are associated with this route table are public subnets because they will have a direct route to the internet through an internet gateway. So this is just what a route table looks like, and you can have many of them, and you can have a lot of different routes in your route table as well. And sometimes they can be difficult to get configured correctly when you're doing it all manually by yourself. Okay, on the last slide, we talked about NAT gateways and internet gateways and VPC route tables, and we showed you how to get your VPC connected to the internet using both public and private subnets. Now we're going to discuss virtual private gateways, and this is how you get your VPC connected to a remote site like your on-premises data center, for example, using a private network connection. So to do that, you can create what's called a VGW, a virtual private gateway, and you can attach that to your VPC. And once you've done that, then you can create what's called a site-to-site VPN connection over the internet to the customer router. And sometimes this is referred to as the CGW or customer gateway. So now that you have this VPN connection, you can run BGP on this VPN connection or use static routing. So you might have a bunch of routes here on the customer side here, and those routes can be advertised via BGP up to this virtual private gateway. And you can enable propagation into your VPC route tables. So all of the routes learned by BGP from this VGW can be propagated into your VPC route table. So that is done automatically for you, and that is the one situation where route tables are automatic in their route additions. Otherwise, it's always a manual update that you need to do to these route tables. Now, these propagated routes are limited to 100 routes, and that is not a limit that you can raise. That is a hard limit, so that's something that you need to think about and potentially architect around. It might be better just to put a route in yourself that says, hey, 10.0.0.0/8, go to my VGW. You could certainly do that and not use route propagation, but again, that is something that you would have to manually do. The AWS VGW or the route tables are not going to do that automatically for you. Now, another thing about this VPN connection is that the throughput is limited to 1.25 gigabits per second, and that is just about as fast as IPsec can go on the x86 machines running in the cloud, like on the VGW. If you wanted more than 1.25 gigabits per second, you could create multiple VPN tunnels and then enable equal cost multipath load balancing across those tunnels to get more than 1.25 gigabits of throughput. But the downside to that is now your network architecture is getting a lot more complex with a lot more paths of ECMP and a lot more things to troubleshoot. So now that you've got your route propagation enabled, now your EC2 instances in your private subnets here can access your customer on-premise data center through this IPsec VPN connection. So this is one way to establish a private connection from your VPC to a remote site like an on-prem data center using your VGW with a site-to-site IPsec VPN connection. Okay, we just discussed using VPN to connect your VPC to a remote site using a private connection. The other way you can do that is with AWS Direct Connect. So what this is going to do is it's going to give you a private dedicated connection using fiber, which could be 1, 10, or 100 gigabits in speed, depending on the direct connect location you are using. And what you will do is you'll connect your customer equipment to an AWS Direct Connect router in an AWS Direct Connect facility. So I established this connection here between my router and Direct Connect, and then what I'll do is create what's called a Direct Connect Gateway, DXGW. I'll create this in the AWS console, and then I will associate my Direct Connect connection with my Direct Connect gateway. And then from that point, what I'll do is I'll associate my VGW in my VPC to my Direct Connect gateway. At this point, I have my Direct Connect connection ready to go. And now what you can do is run BGP on this connection, just like you could with the VGW VPN. We'll run BGP from the customer router here to the Direct Connect gateway. And again, like the VPN, you have a limitation of 100 routes that you can advertise via BGP into this Direct Connect gateway. And then those routes can get propagated, like we discussed in the last slide, automatically into your VPC route table over here. So we've got propagation enabled, and again, we're limited to 100 routes there. And that is a hard limit, cannot be raised. And we want to be very careful with this because if we advertise 101 routes, the 101st route will pretty much break everything. So you want to be very careful of that. So now I've got a much faster connection here with AWS Direct Connect, and that's really great. Now, in the VPN connection we discussed in the last slide, the nice thing about that was the encryption all the way from my customer router into the VPC. You can enable encryption on AWS Direct Connect, but it's going to be limited. Not every site, AWS Direct Connect site, is going to support encryption, but some do. And the encryption that they will enable for you, or that you can enable on this connection, is called MACsec encryption, MAC security. And what MACsec encryption does is it protects the data as it travels on a cable from one device to another. So between my router and the AWS Direct Connect routers, we can enable MACsec there. And that's great. That'll protect me here. MACsec, however, is limited in its security because MACsec only protects data as it's on the cable. As I just said, once your MACsec encrypted data arrives at a device like a switch or a router, the very first thing that happens is that the MACsec is decrypted and your packet travels through these devices in the clear with no encryption. So you do not have end-to-end encryption like you did with IPsec VPN when you're using Direct Connect and you have MACsec enabled. So it would be better from a security standpoint to have an IPsec tunnel travel all the way from my customer router over my Direct Connect connection all the way into my VPC and have my IPsec connection terminated on something here in my VPC. The downside to that obviously is the speed and throughput of IPsec, like we discussed in the last slide, at about 1.25 gigabits per second. So you're making a trade-off for end-to-end security versus performance. Up to this point, we've been talking about how to connect your VPC to a remote site using IPsec VPN or Direct Connect. Now let's talk about how to connect multiple VPCs together, either within the same region or between AWS regions. So you can see here in this example, I have two VPCs on the left, and I want these two VPCs to communicate, and they are in the same region. One thing that I can do is simply create what is called a VPC peering connection. So I went and set this up in the AWS console, and now these two VPCs are basically directly connected to each other, and the EC2 instances can now communicate between these two VPCs over the peering connection. Now I have another region here on the right and another VPC, and you can absolutely create peering connections between regions. So I'll go ahead and do that and establish another peering connection. And now the VPC on the top left can communicate with the VPC on the top right, and that connectivity is working just fine. However, there is a problem in that I cannot use one VPC to transit through to get to another using peering connections. So the VPC here on the bottom left will not be able to communicate with the VPC on the top right by hopping through another VPC's peering connection. That is not supported. So what I need to do is directly connect any two VPCs that I want to communicate with each other. So I'll go ahead and set up another peering connection across the region between those two VPCs, and now I'm looking good. All of these VPCs can directly communicate with each other by setting up a full mesh here. Now I'm going to add another VPC into the picture here. So I've got my fourth VPC in another region, and I want this VPC to also be able to communicate with all of the other VPCs. So I'm going to go ahead and need to create that full mesh by creating 3 more peering connections and making sure that every VPC is connected to every other VPC. You can begin to see how messy this could begin to get at scale. This is just for VPCs right here. Imagine if it were 20 or 50 or 100, how messy that would get with all of these peering connections everywhere. Furthermore, there are limits. A single VPC can only have 125 peering connections, and that's a hard limit that you cannot raise. To be quite honest, I don't know that I would want to manually set up 125 connections on every single VPC. That would be a really painful thing to do. Furthermore, every VPC is going to have a route table, as we've discussed, and that route table needs to have routes pointing to the peering connection to get to the destination VPCs, and that's going to be true for every single VPC. And the route tables in each VPC is going to look a little bit different because they'll have their different peering connections and their different next hops to the destination. So as you can see, this is one way that you can establish connectivity between VPCs, perhaps in a very small environment. Maybe you only have 2 or 3 VPCs and you just want to set up peering connections. You can absolutely do that. But for a larger enterprise that has tons and tons of VPCs and accounts, this is not something that's going to work. So in the next slide, we will talk about another way using AWS Transit Gateway to connect your VPCs together. Okay, I'm a large enterprise and I have a lot of different accounts and VPCs, and I just learned that I could use VPC peering, but that's going to be really messy and configuration intense. It's just not going to scale. So what can I do? Well, I can use a service called AWS Transit Gateway, or the TGW. So the TGW is a service that you can create in a region, and you attach your VPCs to the Transit Gateway, and the Transit Gateway is going to act like a router, and it's going to route traffic from one VPC to another if you have the routing tables configured to do so. Now, the Transit Gateway is only available in one region. I cannot have a Transit Gateway connect to multiple regions, so I have to create another Transit Gateway in another region if I have another region with other VPCs, and I do here. So here on the right, I've got another region with VPCs, so I'm going to create another Transit Gateway in region number 2 here, and get my VPCs in region number 2 attached to that Transit Gateway. Now, one thing that you will notice here is that one of these VPCs has a IP CIDR range that overlaps with the other VPCs. So one thing that the Transit Gateway is not going to be able to do is support that. So I will not be able to attach this VPC here to the Transit Gateway because it has this overlapping CIDR range. Now, if I want the two regions to communicate to each other through the Transit Gateway, I can absolutely do that using a TGW peering connection. So I can peer these transit gateways together across the regions so that I can establish connectivity between regions. Now, as of this recording, the routing between transit gateways over TGW inter-region peering is static routing. So I'll need to make sure that the transit gateways have the right routes pointing to the other region, and those would be static routes that I would manually enter in. Now, once traffic is flowing through my transit gateway, I will not have a whole lot of visibility of the traffic going through that gateway. The transit gateways are not going to be exporting any net flow information. I'm not going to be able to take any packet captures on the transit gateway. So if I'm having trouble with connectivity from one region to another through the transit gateway, I can begin to troubleshoot that, but I'm going to have somewhat limited visibility to help me do that troubleshooting. Now, when you attach a VPC to a transit gateway, you'll need to make sure that the route tables in that VPC have the routes pointing to the transit gateway as their next hop. The transit gateway is not going to add those routes for you when you attach a VPC to it. So you'll need to make sure that you have those route tables correctly configured, and you will have to do that yourself manually. The transit gateway can support a maximum aggregate throughput of 50 gigabits per second from one VPC to another. Now let's take a closer look at what is really happening inside of the transit gateway. What are the different configuration elements that I need to make sure are correctly configured to make the transit gateway work the way that I want it to work? Okay, this big red circle here in the middle is my transit gateway, and we're going to take a closer look at what is happening inside of this transit gateway and how I'm going to be able to set up connectivity the way that I want using the various configuration elements that the transit gateway provides. And the first thing is that the transit gateway has route tables that you can create. You could have just one route table if you wanted and connect everything to that, or you can have up to 20 route tables in your transit gateway. You might be asking yourself, Well, why did I create 4 route tables and not just one? Well, if I want to do some traffic steering through my transit gateway, like isolating some VPCs from others or steering traffic from a VPC through a firewall before it goes anywhere else, you will need to create additional route tables or what are called route domains to set up that traffic steering. So now I've got the things that I want to connect to my transit gateway here. I've got some VPCs there on the left. I've got an appliance or an inspection VPC here on the upper right. And in the bottom right, I've got my on-premises data center with its direct connect connection with my direct connect gateway. And I want all these things to connect to my transit gateway and set up the routing between them. So the first thing that I have here is VPC attachments. So I create a VPC attachment for my VPCs to the transit gateway, and those attachments basically get an attachment number. I can also attach my direct connect gateway to the VPC as well by associating my transit gateway to my direct connect gateway here. Now the next thing I need to do is associate those attachments to a routing table. So I create what are called route table associations. So VPCs C and D there are associated to the same route table here on the upper left. And I do the same thing here for VPC A and B in a different route table here on the bottom left. The reason I did that is because I want to isolate VPCs C and D from A and B. So I'm going to associate them to different route tables. And the next thing I need to set up is route propagation. So when I create an attachment, I will say that I want the routes from that VPC to be propagated into the route table. So I said here for VPCs C and D, we will propagate their routes into the route table that they are attached to. That just basically happens. And then I want to propagate their routes into another route table here that the appliance VPC is attached to. We'll do that for all the VPCs. So that way, any traffic coming from this appliance VPC into the transit gateway, it has a route to get to any of the other VPCs, perhaps to return traffic that was transiting through a firewall. Now for my on-premises, I'm going to be learning a lot of routes through BGP like we discussed earlier. So I can take those routes that I learned via BGP and also propagate those into my transit gateway. And so what I've decided here is that I'm going to go ahead and propagate the routes from my on-premises into this route table here on the upper right so that my appliance VPC can also return traffic to the on-premises data center. And we've got connectivity that way as well. Now, I want to also steer traffic from VPCs on the left through my firewall before it goes anywhere else, maybe to the on-premises data center or the internet. So now I need to create static routes. So you can do that. You can go ahead and create static routes in your VPC route table. So you can see I've done that here. So now any traffic coming from VPCs C and D, I've placed a static route, which points to attachment number 5, which happens to be my appliance VPC over here. So now any traffic that's going to the internet or trying to get to the on-premise data center will be directed through this appliance VPC, inspected by the firewalls. And if the firewall's VPC here has the right routes pointing back to the transit gateway, it'll come back, hit this routing table, and go on to its destination. Now you can see here that I've also added static routes into my VPC routing tables, and I had to do that. The transit gateway, as I explained earlier, is not going to automatically add any routes into your VPC routing table. So I just went in here and go ahead and put a static route into my VPC. I'll need to do that for every VPC and point it to my VPC attachment so that these VPCs have a way to get out. One thing I did not do, which I probably should have done, is also added a default route in these VPCs pointed to my transit gateway as well so that their internet traffic goes through the transit gateway and off to that appliance VPC. Now, another limitation that we have here, but you can do is all of these routes for the VPCs that we learned and the transit gateway, you can advertise those routes over my direct connect connection down to my on-premise data center so that my on-premise data center can learn about the routes, learn about the VPCs that are attached to my transit gateway through BGP. Now there is a 20 route limit, so I can only advertise 20 BGP routes from my transit gateway over a direct connect to my on-premise router. Now, chances are that you probably have more than 20 VPCs, so you are going to have to deal with this limit. And this is a hard limit that cannot be raised. So in order to get around that, what I might do here is I might do some route summarization. So I can go to this direct connect gateway here and basically configure a static summarization of a route that can then be advertised, like maybe 10.0.0/8, and just advertise that. I will have to set that up myself. The Direct Connect gateway is not going to automatically summarize any BGP routes for me. Now let's take a closer look at this appliance VPC. So we showed you how to set up the transit gateway to steer traffic through this appliance VPC. But once it gets inside this appliance VPC, how am I actually going to then steer traffic through those firewalls? And we're going to use an AWS service called the AWS Gateway Load Balancer to do that. And I'm going to show you how that works on the next slide. Okay, let's take a look at a service called the AWS Gateway Load Balancer. And the Gateway Load Balancer is going to help me to direct traffic from my VPCs that are coming through Transit Gateway to a fleet of firewalls that are sitting behind that Gateway Load Balancer. So I can have some high availability and some scale out of those firewalls and have the Gateway Load Balancer basically decide which flows it wants to send to which firewall. So in this appliance VPC here on the right, and this is basically an image that I've used from an AWS blog post on how to set up your gateway load balancer, but I'll quickly summarize it here. What you can see is that we have this gateway load balancer in the middle here, and the gateway load balancer has an endpoint, or basically a network interface into some subnets. And what you can see is that route tables have been created to point traffic to your gateway load balancer endpoint. So as traffic comes in to the transit gateway here from these VPCs, it's going to follow that default route pointing to the appliance VPC, as explained in the last slide. And then once it gets in this appliance VPC, you're going to have route tables that point that default route traffic to the AWS Gateway Load Balancer endpoint. And here they are making sure that the traffic in one availability zone is staying in the same availability zone by making sure that it's pointed to the gateway load balancer endpoint in the right availability zone. The gateway load balancer is also in a subnet that has route tables, and it's going to direct traffic after it's been received by the firewall and processed back out to a NAT gateway over here for internet traffic. It also has routes that have been programmed in to get back to the VPCs, to the transit gateway, and so on and so forth. Then I've also got another route table here for the NAT gateway to send internet traffic to the internet gateway, as well as sending traffic back to the VPCs through route table entries. You can begin to see that there are a lot of different route tables here that need to be set up correctly, even over here on the VPCs here on the left. So a lot of different route tables to correctly configure. You are going to have to do this manually yourself. And then once you've done all of that, then you have traffic steering through your AWS Gateway Load Balancer. Gateway Load Balancer will receive the traffic, create a tunnel between itself and the firewall using the Geneve encapsulation. The firewall will unencapsulate that packet, do its processing, and send it back to the Gateway Load Balancer. And the Gateway Load Balancer will deliver it back into the VPC from which it was received. And then the route tables will be followed then at that point to get the traffic where it needs to go. So this is the AWS Gateway Load Balancer that you can use in AWS to steer traffic through a fleet of firewalls, for example, in an appliance or inspection VPC. Okay, if you remember earlier, we talked about AWS regions and we talked about the availability zones within a region. I want to take a minute to discuss AWS local zones because these are relatively new. So what is an AWS local zone? Well, we already know about the AWS region and its availability zones, and there are certain places in the world. And so, for example, I have a region here in Oregon, and I've got my availability zones, and I can build and run applications here in the Oregon region. Now, I may have users in other part of the country that want to use that application, for example, in, let's say in this example, Los Angeles. So for your users in Los Angeles, the nearest AWS region might actually be the region in Oregon, which is fine, but there's still some latency between Los Angeles and Oregon. So the users here in Los Angeles will be able to access the application, but their experience is going to be not quite as good as users who might be living closer to the region. There'll be additional latency there. So maybe the application that I'm building here is a low latency application, and I want to give my users in Los Angeles a better experience. So that is why AWS created what is called a local zone. So a local zone is basically a smaller version of an availability zone in a metro area closer to users where there is not an AWS region really close by. So in this case here, there is an AWS local zone in Los Angeles. So a local zone is created And that local zone is then attached to the region. So really the local zone becomes an extension of the AWS region. And now you can choose to launch your applications and EC2 instances in that local zone. And now your users in Los Angeles will have a very low latency connection to your application, which is still running in this Oregon region. It just happens to be in this local zone that's very close to them. So with the local zone, what you can basically do is take the VPCs that you have running in the region and extend them all the way to the local zone, basically extending your VPC closer to the users that are using that local zone. So the same VPC that's in Oregon is going to exist in my local zone. Now the way that I use a local zone is I'll go ahead and create a VPC subnet in that local zone. And just like any of the other availability zones, a VPC subnet is specific to its zone that it's in, and that's the same with a local zone. So when I create a VPC subnet in my local zone, that VPC subnet is only for that local zone. So now I've got my VPC extended with multiple subnets. One of those subnets just happens to be in my local zone. What I cannot do is take a VPC subnet from the AWS region in Oregon and extend that to my local zone. There's not going to be any kind of VPC subnet stretching like that. And I can also do that again with other VPCs. I have multiple VPCs in the Oregon region, and I can simply extend those VPCs to my local zone by simply creating a VPC subnet in that VPC in my local zone. Now, not all of the services exist in a local zone, and one of those services that does not is the AWS Transit Gateway. So if I want to use the AWS Transit Gateway to route traffic between these two VPCs that I've extended to my local zone, I'll have to be mindful that that traffic will have to go back to the AWS region to be routed through the Transit Gateway and then get back to the destination subnet. Now, what I can simply do is create multiple VPC subnets in a VPC, and I can get local routing between two VPC subnets in the same VPC in my local zone. That will work just fine. If I really wanted to have multiple VPCs and route between them locally, one thing I could do, like we explained earlier, is create a peering connection between these two VPCs here, and then I will have a local connection between the two VPC subnets and the VPCs here in my AWS local zone. Another new type of zone is a AWS wavelength zone. And a wavelength zone is very similar to a local zone in its sense that it's going to extend the AWS region closer to users to give them a better low latency experience. However, in this case with wavelength, it's a focus on mobile users and mobile devices in a wireless carrier's network. One of the challenges with mobile devices as they go through a wireless carrier and try to get to a region is that there's a lot of different hops through the carrier's network and different internet connections before that traffic ultimately arrives at the region. So these users here can experience higher latencies, lower throughput. And if I'm building an application that I want to have very low latency with my mobile devices, this is not going to work very well. So an AWS wavelength zone is basically a miniature AWS availability zone that is built inside of the wireless carrier's network. So now you can launch and run EC2 instances that are basically in the carrier's network and give your mobile devices and users a very short path between themselves and your application running on EC2. Now, similar to a local zone, you can basically take your VPC and extend it to the wavelength zone and create subnets that are in that wavelength zone and only in that wavelength zone. And all of the same considerations apply in the sense that not all of the AWS services run in a wavelength zone, including the transit gateway. So if you want to route traffic between VPC subnets, you'll have to all the same considerations around traffic routing that we discussed earlier with local zones. Now, on-premises data center connections can be connected to the AWS region through Direct Connect, as we explained. However, maybe you want to have lower latency access from your on-premises data center to your AWS services. Maybe your on-premises data center is somewhere in Los Angeles, for example, and you're connecting to the Oregon region, and you would like to have lower latency access to EC2 running in the region. So AWS Outpost is a service that allows you to run AWS services like EC2 and RDS on a rack of equipment that is installed into the customer's on-premises data center to provide low latency access from your on-prem servers to AWS services running in a rack of equipment right in the facility. So this is a way, again, like local zones and wavelength zones, you can extend the AWS region closer to your users and applications and devices. And again, all the same concepts around traffic with extending VPCs. You can extend a VPC from the region to your AWS Outpost, and you can create subnets on your AWS Outpost that only live on your AWS Outpost. It's like your AWS Outpost is a little miniature availability zone. And not all of the services are available in Outpost, including the AWS Transit Gateway again. So if you want to route traffic between two VPCs on an AWS Outpost, you can use a peering connection, or you can just use a single VPC and just route between subnets. But all the same traffic considerations apply when it comes to multiple VPCs on an outpost as well. So earlier we discussed the AWS Transit Gateway and how it can route traffic between multiple VPCs and within a region. And I don't need to have a big messy full mesh of peering like I do with VPC peering connections. So all of that is really good and nice. Now let's take a minute to discuss some of the challenges, both from an operational and visibility standpoint, that you might experience when using the AWS Transit Gateway. First is that the AWS Transit Gateway is a basic layer 3 routing device, and that's really all it is. It's going to look at the destination IP address of the packet. It's going to make a decision on where to send it next. It's not going to have any capabilities around defining layer 4 type rules or any kind of stateful firewall rules. So if you need any kind of granular security rules that need to be checked before routing between VPCs, Transit Gateway is not going to help you there in any way. We discussed earlier too how to steer traffic through the Transit Gateway using route tables and attachments and route propagation. And you can certainly do that, but it's a manual and complex process, especially as the environment scales and you get a little bit more in terms of variations in how you want to steer traffic. So you are manually creating route tables and domains and deciding where to propagate routes. So you can certainly do all that, but it can be quite complicated to do all yourself manually. And the VPC route tables themselves, the Transit Gateway is not going to manage or touch your VPC route tables. So you will need to go to your VPC route tables and make sure that they have the right routes pointing to the Transit Gateway, and you're going to do that yourself, both between VPCs as well as from your VPC to on-prem. Now, from a visibility standpoint, the Transit Gateway is like a black box in that you really don't have any access to see what's happening inside of it. Any traffic that's flowing through the Transit Gateway, you are not really going to get any NetFlow exports to NetFlow dashboard. Any of the flows going through the Transit Gateway, you will not be able to see what flows it's processing at any given time. So you're going to have some limited visibility there when it comes to troubleshooting connections or to actually just get some visibility around traffic rates and flows. And then when it comes to connecting with BGP, we've talked about some of the limitations there around the number of routes. So you are limited with the number of routes you can advertise from a Transit Gateway to on-prem, and that is 20. Chances are you're going to have a lot more than 20 VPCs connected to it. So you have more than 20 routes, and you'll have to set up some BGP route summarization yourself on the Direct Connect Gateway. The Transit Gateway is not going to do that summarization for you. You are going to have to set up that yourself. And then you have the 100 routes that you can send from your on-prem to your Transit Gateway using BGP. You have to be very careful with that one because if you send a 101st route, it's going to break everything. So that you want to be very careful not to get close to that. So you might need to set up some route summarization on your customer router as well. Now the Transit Gateway also does not pass any BGP attributes from one BGP neighbor to another. Once it receives a BGP route, it installs those routes into its route table, and those route table entries really do not have any BGP attributes along with them. So when the Transit Gateway goes to advertise those routes to another neighbor, it's just basically going to do a normal BGP advertisement with no route attributes that were received when that route was received originally. So from a routing standpoint and visibility and basic layer 3 connectivity, those are some of the challenges that you may face when using the AWS Transit Gateway. Now let's talk about AWS Transit Gateway Connect, or otherwise known as TGW Connect. TGW Connect lets you run a routing session with your TGW over a GRE tunnel. Now, why would I want to do that? Well, consider the scenario of maybe an SD-WAN or some kind of network virtual appliance running on an EC2 instance in a VPC, and you want to exchange routes between your TGW and this NVA, and then SD-WAN is a good example of that. So the first thing I'm going to do here is I'm going to connect this VPCe here that has my SD-WAN virtual appliance. I'm going to attach that to the TGW just like I've attached any of my other VPCs to the TGW. So at this point here, nothing is really different. But now I want to run routing between this network virtual appliance and my TGW. So the next thing I'm going to do is I'm going to define a TGW Connect attachment. And so what I'm saying here is this attachment that I made between VPC and TGW, I'm going to define that as a TGW Connect attachment. And once I've done that, what I can do at this point is then define a TGW Connect peer, which is really a GRE tunnel between the TGW and this network virtual appliance. So by defining this connected attachment, the TGW is going to let GRE packets arrive on that TGW attachment to establish this GRE tunnel between itself and the NVA, which we define as a TGW Connect peer. And on this TGW Connect peering, we are going to run BGP over this GRE tunnel between this NVA and the TGW so that we can begin to exchange routes now between this SD-WAN virtual appliance and my transit gateway. And when I do that, the TGW can exchange a lot more routes than normally would. For example, in the direct connect that we discussed earlier, a basic direct connect connection, we had limited routes there, but with TGW Connect, you can advertise up to 5,000 routes from a transit gateway to a network virtual appliance, in this case, using TGW Connect. And the virtual appliance can advertise up to 1,000 routes from itself to the transit gateway over this TGW Connect peering. Now, TGW Connect also supports direct connect and connectivity to on-premises data centers. So we've already discussed how you can use AWS Direct Connect to connect your on-premises data center to your transit gateway using a normal Direct Connect connection, and we learned that there are a limited number of routes when you do that. You can only advertise 20 routes from your transit gateway to your on-premises data center, and from the on-premises data center, you could only advertise 100 routes to your TGW. Now, let's say I need a lot more routes, so I might want to use TGW Connect for that. So what I'll do is I'll simply take this direct connect connection to my TGW, and I'll also define that as a TGW Connect attachment. So again, that's going to let us run GRE over that TGW attachment. And then I will define a TGW Connect peer over this direct connect, which is going to be a GRE tunnel between the transit gateway here and my on-premise customer router or some other device that can run GRE. And just like we did above, we are going to run a BGP peering session over this GRE tunnel for the transit gateway to exchange routes with the customer router. And by doing that, the transit gateway can advertise a lot more routes than it would in a normal direct connect connection. In this case here, it can advertise, like above, 5,000 routes from the transit gateway to the on-premise customer router over this GRE tunnel. And the customer router can advertise up to 1,000 routes between itself and the transit gateway over this TGW Connect peer GRE tunnel. So as you can see, Transit Gateway Connect is really useful in establishing routing between some kind of network virtual appliance and a VPC, for example, an SD-WAN. And it can be used to exchange a lot of routes over those tunnels. So if you may need a lot more routes exchanged between your on-premise data center and your transit gateway, you might consider using TGW Connect to do that. Now, TGW Connect does have some things to think about. The first thing is that it's GRE. You are running the GRE encapsulation between the TGW and some other device. And GRE may only be able to go so fast. Well, in the case of the transit gateway, that tunnel can only go up to 5 gigabits per second. And you'd also have to look at your network virtual appliance or your on-premise customer router to see if it can support GRE and how fast it can do GRE and so on. And also there's the additional complexity of adding these TGW Connect attachments and then these additional BGP peering sessions over the GRE tunnels, adding a little bit more complexity to your network architecture. But if you really need to have a lot more routes exchanged between an on-premise data center and TGW, or you need to set up routing between an SD-WAN and your transit gateway, then you would use TGW Connect to do that. There's also a new networking service by AWS, and it's called AWS CloudWAN. Now, earlier we discussed a lot of the challenges by using the transit gateway in terms of its manual configuration to provide isolation between VPCs and environments and steer traffic through inspection VPCs. We also discussed how you can peer transit gateways together over regions and how that is a static routing configuration. So AWS CloudWAN is a service that helps to automate some of those things for you and help you use AWS as a global WAN for all of your remote sites and your VPCs. So basically what it's going to do is it's going to orchestrate the segmentation and isolation of your VPC environments. You can create different segments here logically, like development, production, and shared. And then it's also going to orchestrate the network peering between the different regions. So you can say, look, I want to use these few regions here, and I want to have these segments. And you're going to describe that in a JSON policy document. You're going to say what regions you want to use, what segments you want to have, and which segments should be able to talk to which other segments. And AWS CloudWAN is going to go ahead and set that up for you. It's going to set up the peering. It's going to set up all of the isolation between those environments just by reading that JSON policy document that you provided to it. Now that's very nice, but again, this is a AWS only way of doing things. So if you are AWS only and you know that you never will use any other cloud, then maybe CloudWAN might be a way for you to help automate some network connectivity between your regions and environments. But if you have another cloud provider presence, the way that that is going to work in another cloud provider is going to be entirely different. So you will be managing two different areas of policy and connectivity, which could be a challenge. Now, CloudWAN is also basically transit gateway under the hood. So it has these concepts of core network edges, which live in the regions. And those are basically no different than the transit gateway in the sense that there's very limited visibility and troubleshooting with those. You're not going to be able to take packet captures from your core network edges or see the individual flows that are flowing through it. And AWS CloudWAN is not free, so you will want to investigate the pricing of AWS CloudWAN and maybe investigate other alternatives before you make a decision on whether or not you want to use CloudWAN as your basic global network policy and configuration. Okay, so far we've learned a lot about the basic networking constructs of AWS, including the VPC, the VPC route tables, security groups, VPC peering, and transit gateway. Now let's take a quick look at what are some of the other AWS networking services to be aware of. One of those is AWS Elastic Load Balancing. So you can create and deploy AWS load balancers into your VPC using Elastic Load Balancing. And there's different types of load balancers that you can deploy, such as an application load balancer or a network load balancer. And the difference between those is the application load balancer is looking more at the application flows, and the network load balancer is really looking more at the IP addresses and the layer 4 flows. Then you also have interface endpoints. An interface endpoint is where you can basically deploy a network interface into your VPC subnets, and those network interfaces give you a path to an AWS service in the region like S3 or some other service. So what this does is it gives you a private connection to, for example, here, S3, where S3 will basically have an endpoint with a private IP address in your private subnet. So you have a more private connection there to your data stored in S3. Then there's also AWS Private Link, which uses endpoint technology again. So you basically can deploy a service to another customer, and that customer, when they want to consume your service through Private Link, an endpoint will be deployed into their VPC, and that endpoint will run through your Private Link, which is associated to a network load balancer. And that way they can access your application through a private IP address in their own VPC, and they don't have to worry about any other connectivity to your VPC and any routing or overlapping IP addresses that might happen from that. Then there's also Amazon Route 53, which is a DNS service. So you can create DNS zones that resolve to IP addresses in your VPC. And this is a global DNS service. So your customers anywhere in the world can resolve domain names that resolve to IP addresses in your VPC using Route 53. AWS Global Accelerator is a way for users to get onto the AWS Global Backbone as soon as possible when accessing an application in your VPC. So one thing you can do is you can take a network load balancer and associate it to AWS Global Accelerator. So when a customer somewhere out in the world is trying to get to your application through your network load balancer, they will get onto the AWS Global Backbone at whatever local edge location is closest to them, and then they will have a better network connectivity from their AWS edge location all the way into your region using AWS Global Accelerator. And similar to that, Amazon CloudFront is a way to cache content at AWS edge locations all over the world so that static content is closer to your users so that when they're accessing your website, for example, that might be running in your region, they can access cached images and content on Amazon CloudFront and get a very fast response from your website. And it also reduces a lot of the load on your web servers in your VPC because Amazon CloudFront is providing a lot of that cached content to the user closer to them. This concludes the introduction to AWS networking. I want to thank you very much for your attention during this section. Next, you will go into an introduction to networking in Microsoft Azure.